Okay, good afternoon, everybody. I see people are still trickling in, so that's going to be a feature for the foreseeable future, I think. And welcome to our monthly book seminar. Today we have two guests. We have Pranay Kotasthane. I'm really sorry, I keep mangling names, and Abhiram Manchi, who wrote a book on a topic that is pretty much on a lot of people's minds when we are in this sphere. The book is called When the Chips Are Down, a deep dive into a global crisis. Obviously, and they say it sort of in the blurb as well, that we didn't really used to talk much about chips, about semiconductors, and our world has pretty much changed a lot in the past couple of years, when increasingly we are now relating to this the technology that is basically in everything, gets smaller and smaller, but also gets bigger and bigger in terms of geopolitics, because it is now fully fledged an item that is in geopolitical strife. We're going to get a different perspective from, for example, an American or a Dutch perspective. You're probably aware that the Dutch have a perspective on this too, hosting ASML, for example, and being wheeled into all kinds of geopolitical coalitions, for example, with the United States. Maybe those will come up as well, but first I'm going to give the floor to our speakers. Pranay, I'm going to give the floor to you. You can introduce yourself shortly, also your co-author, Abhiram, and take it away. You will talk for roughly sort of 30 minutes, 40 minutes, and then we'll keep the rest for our discussion. Pranay, the floor is yours.
All right. I hope I'm audible. Yeah. All right. So I'll begin. Hi, everyone. Glad to be talking to you all. I'm Pranay, and both of us, Abhiram and I, have worked in the semiconductor industry in the past, being in Bangalore. And as Dennis said, actually, not just in the geopolitical sphere, but also in the technology sphere, semiconductors were hardly talked about, because in India, a lot of talk when we say technology is about software and software services, and semiconductors, the industry just worked so well that no one had to bother about the underlying infrastructure that runs it all, right? And then things started changing. In 2019, first, there were a few export controls which came on Huawei, ZTE, etc. And that's when we started observing this industry more closely. And we are both also trained in public policy. So the lens that we bring into this book is largely from a public policy and foreign policy perspective. And instead of focusing on people of the industry, our focus is largely about trying to understand some of these questions which are there on the screen, to look at, to build a framework to understand why semiconductors are important from a geopolitical perspective, to understand why some of the players from a public policy perspective became more powerful than others. What were the ingredients which which were there in some countries' ecosystems and which weren't there in some others, like the USSR and initially China also. Third, yeah, we we've discussed about China semiconductor industry, the trends and how that is going. And finally, we try to take a guess at what are some of the future politico-economic instruments that we might see in this domain. So that's what this book is about. So we always begin with TLDR. So if you have to drop out of this session after 5 minutes, I'll give a summary of what this book is about. So these are some of the main key highlights from the book. One, we write that semiconductors are not just critical, but they are metacritical. And we write about three imperatives: geopolitical, geoeconomic, and technological. And we write that it is the confluence of these three imperatives which has made semiconductors enter the domain of geopolitics, not just now, but also sometimes in the past. And Abhiram will discuss some of that. Second, people have heard of this prediction called the Moore's law, a prediction which has lived for so long that it's now termed a law. But it is a result not just of technological strides, but equally of economic innovation and globalization. So that is also an element which is not often discussed, but we write about that at length in the book. The third one is that every country which has built some sort of a local semiconductor industry began with some kind of technology transfer / collaboration with the US. So that is also an important part, including China. The fourth part is value addition contributions across the three main stages, which are design, manufacturing, and assembly, have changed significantly over time. So the normal conception of all this is the U-shaped curve, right? That design captures the maximum value, manufacturing and assembly have low value addition, and finally there is value addition on top of the services that are there, the software, etc. But in the semiconductor industry, that has changed over time. So you will now see that manufacturing adds more, contributes more value addition than design does. And we'll discuss that as well. So this is an interesting dynamic if we zoom into the semiconductor industry. The fifth one is that government-run projects to build manufacturing capabilities have similar root causes of failure, whether it is USSR, China, or India. And we'll discuss some of that as we go ahead. In looking at the future, in this domain, nation states can, according to us, pursue four kinds of strategic goals. They can either try to deny access to an adversary, try to outpace an adversary, or simply try to build supply chain resilience without targeting a specific adversary. Or finally, some nation states, it has been alleged, have also tried to influence minds through hardware espionage. Finally, our conclusion is that interdependence is unlikely to go away over the next 2 decades, despite the massive investments which are happening across geographies. So this is what our main key conclusions are from this book. Now, this is how we thought we'll shape this presentation. We'll start off with discussing some standout features of the semiconductor industry. So I'll briefly discuss that. Then Abhiram will discuss some of the characters or some of the key nation states involved in this industry and how their ecosystems have been built. Then I'll discuss the present moment and why we call semiconductors as metacritical. And finally, we'll discuss some future and some of the instruments that you might see being deployed in the years to come. Now, these are some of the four standout features that we think make semiconductor industry at least different from some of the other industries that we know of. Right? So one is that because of the fast growth in semiconductor technology, we have certain expectations about electronics that we don't have for anything else, right? So many people have given this comparison, but for example, we don't expect our cars to go 2x faster every 2 years, but we do expect our laptops and our mobiles to go 2x faster every 2 years, right? And a lot of the software, etc., also relies on the fact that we are trying to make products which are faster and growing at breakneck speed year on year, right? So the famous prediction in 1965, when Gordon Moore was at Fairchild Semiconductors, was this, right? That the number of transistors will double about every 2 years. And in 1965, he was able to foresee that you might have wonders such as home computers, automatic controls for automobiles, and something which he couldn't term as the mobile phone, but a personal portable communications equipment, right? So this is sort of one idea. This prediction becomes one guiding light for the entire semiconductor industry, and through technical and economic innovations, this has been kept true for almost 40 years, right? So there have been versions of it. There have been many times when people thought that Moore's law is over, and if you just Google Moore's law is over, you can go back to many decades, and yet we see that it is alive in one way or the other. So what happened is innovation moved from design, and then there was an era when people thought that Moore's Moore's law is over, but then the innovation and value addition moved to manufacturing. And as we speak, we are now thinking of new innovations in packaging, which will probably keep this scaling alive for a few more decades. So this prediction itself was said when IC just had about 64 transistors, whereas now if we talk about an A14 chip, it has 134 million transistors on a per millimeter square area, right? So that's how the technology has scaled, and this scaling really also becomes a default for the way people think in this industry about how change can happen, and a lot of defaults are about improvements rather than thinking about this will peter out one time or the other. So this is a very interesting part of this industry which we must keep in mind. The second one, of course, is the supply chain itself. And we always think that, semiconductor industry is like sort of a poster child for what economists call comparative advantage based specialization. There are quite a few factors which have gone into play, right? So initially when the industry started, obviously the model which existed was called the integrated device manufacturing model, which is the same company used to do designing, then used to do manufacturing, finally assemble, package the chips and ship it out, right? So this was fine, but as we progressed in towards Moore's law, and as we tried to pack in more and more transistors and more smaller transistors within the same area, the flip side to the Moore's law is something called the Rock's law, and which came into play as well, right? So the Rock's law says that approximately the capital cost for the next generation of advanced chips also doubles every 4 years. Right? So we had this interesting flip side that you wanted to do more and more with the same silicon area, but to do that your capital costs had to keep doubling every 4 years. This became very costly for companies starting the 1980s, and not every company could take that kind of costs. So the result was something called comparative advantage based specialization. People in Taiwan, initially some ASIC developers in US, Europe as well, but largely it started gaining traction when TSMC promised two things to some of the customers. It said that one, we will never compete with you, and second, that we'll never compete with you in the design segment. And second, they said that whether you are Broadcom, whether you are Qualcomm, whether you are any other company, but you only give us the designs and we will do contract manufacturing for you at so you don't have to take that hit of the Rock's law, we will take it for you. So this was a very interesting dynamic which led to the next big jump. And this also coincided with economic globalization. So many companies in the US, Europe were also happy to let manufacturing go to other places because at that point of time, manufacturing didn't have a very high value addition, and also manufacturing high capital cost, low value addition, and at that point of time it was also somewhat environmentally polluting, right? It has improved a lot now, but that time these were the factors at play. So this comparative advantage based specialization worked really well, and I'll just discuss some of that very briefly. So design, as we all know, is a largely a human capital intensive process where blueprints of chips get made, and today it accounts for roughly 33% of the value addition. US is a dominant player, and some of the common company names in this you already know. So the next stage, of course, is when these blueprints are handed over to contract manufacturers, like I mentioned, TSMC or UMC. And these are it is a capital intensive stage where blueprints are converted into physical wafers. Now, interestingly, today, this segment accounts for nearly 56% of the value addition, if you include the equipment, materials, etc., which are involved. East Asia is a dominant player here. And of course, Dennis mentioned ASML, manufacturing equipment suppliers also have a role. The third stage is, of course, assembly, testing, and packaging. And this is also a capital intensive stage, but not to the level that you require in manufacturing. This stage also requires a lot of skilled labor. But so this is largely, we classify it as labor intensive, and ICs are assembled and packaged here. Today, it accounts for 12% of value addition, and we can expect this to rise. As I mentioned, a lot of innovation is now happening here to keep the Moore's law alive. And some players here again are Taiwanese and Chinese players. So this is a chart from A.T. Kearney, which sort of tries to look at how the value addition happens across countries and across segments. So you can see that the core fabrication is 34% and the core design is 30%, right? And if you add the fab materials, the fab tools where ASML, etc. comes in, it's definitely more than 50% now. So that's interesting. And this dynamic makes, I really like this analogy which Willie Shee talks about, that because of this comparative advantage based specialization, you have an extremely efficient industry, but it is also subject to geopolitical shocks or other shocks, right? So that's why he calls it a transcontinental relay race with hidden hurdles. So companies do some part of this entire industry. No country is self-sufficient in chips. Even Taiwan's biggest imports are ICs. So they do one part of it, and then they pass the baton to the next company in another country. So this works fine in most cases, but when there are geopolitical impediments, etc., there are hidden hurdles. And today we are seeing these hidden hurdles become unhidden as geopolitical and geoeconomic considerations collided over the last 3-4 years. The third important element is just that the civil technologies here are far more cutting edge than the military ones. And you can see that some of the most advanced chips that we talk about aren't going into our military ones upfront. First, they go into civil technologies, because the demand that you require for justifying a $12 billion investment on your latest fab can only come if you're serving commercial players, which will have much larger demands than military applications like defense and space. Finally, big investment and knowledge decades really matter in this industry, especially for manufacturing. And that's why government-run projects of USSR, China, India have fallen behind. All of them had made promising starts, but as they started hitting Rock's law, they all fell behind because governments didn't see the logic of putting a lot of capital investment every 4 years. Also, competition came to be seen as a liability when you have governments running multiple fabs. And why would a government put billions of dollars in an industry which requires recurrent capital investment? Finally, in countries like India, even foreign exchange became a constraint. So these are like 4 important elements which I just wanted to highlight, and it sets the stage to understand some of the other elements in semiconductor geopolitics. Abhiram, over to you for the history of other countries.
Yeah. Thank you, Pranay. Thank you for setting the stage. So what we felt was that it was important to understand, the different players in the industry and try to get a sense of how each of these players actually came into being and actually ended up where they are right now. So we're talking about competitive advantage-based specialization, right? So how did each of these country get that competitive advantage? So we'll be starting out talking about the United States at the beginning. And if you look at semiconductors in general, I think United States has been leading the pack since the beginning and has been the most innovative. As Bill Gates had once said, my first stop on any time travel expedition would be Bell Labs in December 1947. So December 1947 was when the transistor was actually invented at the Bell Labs. So if Bill Gates ascribes such a huge value to it, we need to understand why. So what is a transistor? It is a switch. It is the building block of a chip, and this particular switch, if you think about it, it regulates the flow of current. And on the image on the right will give you a better idea. If you remove the red flag on the left, the current starts flowing on the right side. So this simple circuit grows into adders, subtractors, multipliers, and that grows into the chips that we have today in our phones. All the complicated machinery that we are so used to in our phones and laptops, it comes from this simple logic. And it started out from Bell Labs. I think we considered that it was the confluence of the greatest minds of those times, all being in the same place and working on challenging problems and trying to fix them in systematic ways. That is what led to such cutting edge technological developments by the US at the beginning. And to add to that fact, post 1960s, 1970s, there was the Cold War era, where that it was getting heated up a lot. And I think the first, I would say the first start was with the Sputnik crisis, where it was a shock to US. And you could say that essentially the US did not expect such a huge technological development from the USSR at that time, and it led to a flurry of investments in the hundreds of millions of dollars into science and technology and education, and it led to NASA and DARPA as well. This is what we have termed as creative insecurity in our book, where we talk about uh, essentially US be feeling creatively insecure, and they do not want to be left behind in the technological race. And even though there is no war per se, they would still want the technological development and they would still want to be on top. This can again seen with the case with Japan as well in the 1980s and 1990s, when Japan starts making a lot of memory chips. US starts feeling creatively insecure again, and then starts investing a huge amount of money into industrial policy, trying to set up what is called the Fab 14 or the Sematech, where it banded together 14 of the top semiconductor firms to collaborate with each other and try to come up with innovative solutions to beat Japan at its own game. And when that worked to an extent, they started with a policy as well, keeping price floors and price hikes, and trying to make sure that they have a set percentage of sales in Japan as well. So there has been an interplay between government and the semiconductor industry from the beginning, right from the times of NASA and DARPA, with a lot of military funding into the industry as well. So as much capitalist as USA is, there has been a significant industrial investment. And we see that currently as well with the CHIPS Act proposing 52 billion being spent on semiconductor industry in different aspects in designing, manufacturing, and packaging as well. The current status is that they have a strong stance with China. They're blocking they're limiting the use of chips, very advanced chips in China. They have a monopoly on what is called EDA, the software which is used to design chips. They have control over the architecture, and they have allied positions in manufacturing and assembly. So essentially, they're in a very good place now. So next, we'll move on to the next countries. That is, we're going to talk about the European Union next.
Yeah,
Pranay,
I just wanted to add that creative insecurity is a term often used in politics of innovation literature, and Mark Taylor's book called The Politics of Innovation is one which debuted this concept, and we've referenced that in the semiconductor context for this book. Over to you, Abhiram.
Yeah. When talking about Europe, what started out was that initially Europe did not have as much military funding as the US did, so the growth was slightly limited. There have been pockets of development across different countries in Europe, but not EU as a whole. First would be to talk about Zelenograd in Russia, which was Russia's chip city. They had huge sums of development, huge sums of money put into development of a city specifically for microelectronics and semiconductor development. But they went about it in a wrong way. They would bring in chips from Texas Instruments and Fairchild Semiconductors, and would try to figure out what they were doing and try to recreate that chip. So they were always 2 steps behind what the US was doing, and to a great extent, it was largely government funded, and government was again the sole customer of it. So the scale essentially did not make sense, and currently we don't know the ongoings of what exactly is happening in Russia with respect to semiconductors, but it is safe to say that it is nowhere near it has nowhere near the technological capability that US has. And we have other countries here, and I've listed out a few of the top firms. You have Philip, ASML, IMEC Belgium. ARM is the UK, but I've just clubbed it with Europe. You have Infineon from Germany, NXP, Siemens, etc. So what I would say the Europe has gone on to do is try to find a competitive advantage where they don't have to compete on scale and compete on investment, but they would find specific hotspots and try to make themselves the best in that. And there are 3 main important companies that we have discussed in the book. One would be ARM. Um, if you talk about instruction set architecture, there are 2 main instruction set architectures which are used in semiconductors today, and those would be x86 and ARM. x86 is what is used by Intel, that majorly constitutes your desktop architecture, and ARM is primarily used in your mobile devices, which I mean, Apple is using it for their MacBooks as well, but it started out with mobile devices, low power devices, and it grew into laptops as well. So ARM has a huge power in the market and a huge, I would say almost all mobile devices are essentially using ARM right now. And this gives them good leeway, and it gives the UK a good political advantage as well. When Nvidia was trying to acquire ARM, the UK government actually put a stop to it because it had national importance. The company had immense national importance for the UK. So yeah, the US essentially is in control of x86 and also is allied with the UK, so it has a good relation with ARM as well. So you can see how US is in such a good position. And we're talking about ASML. I think for the people in the Netherlands, ASML is nothing new. They have such a huge market, and they're doing EUV deep lithography machines. So these machines are used for manufacturing 99% of all cutting edge chips. And IMEC Belgium as well, they are known for their research. The kind of research that they do is 10 to 20 years into the future, and literally every company in the semiconductor space works with IMEC to see where the future of this is. Next. Next, I want to talk about the East Asian countries here. It starts out with Japan. Post-war Japan was a mess, and because of its Cold War interests, US actually starts helping out Japan, and it could be technology transfer, it could be money, or it could be just access to US's market. Japan benefited in a huge way. And Japan also started putting in a lot of investment into semiconductors with the VLSI project, which we talk about more in detail in the book. And as they were good with operations and supply chain, they were able to get a higher yield in semiconductors, and they began to take over US in memory chips, and as such hold a name for themselves. And the other one would be Taiwan. Similar to Japan, it's again related to the Cold War. US wanted to stop the spread of communism to the east, and Republic of China was the best place to start. Taiwan was one of the first countries to set up the world's first SEZ, and that started the zero tax regions. And this is where US would again do knowledge transfer and again give access to the market. And Taiwan essentially started out with packaging and set up publicly funded government research institutes, which were very open to people leaving the research institute and starting out their own. This is how TSMC, UMC, and most of the major Taiwanese companies started out. The third one would be South Korea. South Korea has been US ally since the Korean War. Once the Korean War ended and the country split into two, and the same way it started out with packaging and with US's help. The difference between Taiwan and South Korea being South Korea, incentivized all these big major corporations such as Samsung to, Samsung to invest in semiconductors and grow. So they wanted the risk to be taken by the private sector majorly. So that also worked out in their own way. And South Korea and Samsung, as you know, is currently leading the pack. And Singapore and Malaysia is kind of similar, the export-led growth and foreign companies coming in. Next. Next would be China's juggernaut. We talk about how and in what kind of amazing position China is right now and how it is being affected as well. China is kind of a double-edged sword right now. So it first started out with integrated circuits under Mao Zedong, but it didn't work out during the Cultural Revolution. And once Shenzhen was set up and SEZs had come in and China's quality of life improved, people started coming back and they saw the potential. And China started started with packaging and manufacturing at the lower nodes. They don't do cutting edge. They didn't do cutting edge at the beginning, but they started out with the lower nodes, which are much more inexpensive and more labor intensive. And that worked out very well for them. I've on the right side, I've drawn a small picture of Huawei on how it started out as the world's biggest smartphone vendor. And initially AT&T's deal collapsed, and then there were new sanctions against against Huawei in the US. There were allegations against Huawei for espionage and a lot of issues. And that eventually went on to encapsulate the Chinese market entirely, Chinese companies entirely, and US started banning a lot of Chinese companies from access to software, access to chips, and everything. So yeah, China is in a very difficult position right now because of how strong US is and the kind of monopolies US has. But still, when you look at the lower nodes and the kind of scale that China builds in, they'll be able to do well in that segment. Yeah. And talking about India, initially India started out with SCL, Semiconductor Corporation Limited, and it was government funded, and the sole person were giving their chips to was again the government. There was no competition. There was limited demand, and it couldn't grow as much. There was a large fire as well, meaning that India would then fall back. Then again in the early 2000s to 2010, there were again multiple trials with AMD's Fab City, JP Group, and Cricket Semiconductors. But due to the regulatory environment and due to the bureaucracy or some other issues coming up due to the delays, it never worked out. India is trying heavily right now. They had announced a $10 billion plan to set up semiconductor manufacturing and packaging in India. And it might be different this time because the regulatory environment is different, and that is what has been addressed as well, from the investment landscape to the embracement of technology in India. The government feels that this is the right time to step in and work on semiconductor manufacturing. And India is also a very strong design powerhouse. All major companies have set up in India, and there are huge offices and engineers working solely for the semiconductor design here. Yeah, I think the next two we'll be going to talk about what is the current present situation, which I'll give back to Pranay.
Yeah, so I'll be quick on this. So now we'll discuss briefly about the present and then I'll end with the future part. So right now, we think that this is a limited denial regime, whatever we are seeing. I think the war metaphor often has more to do with aligning domestic policy vectors rather than achieving foreign policy objectives, because once it is framed as a war, then you can align domestic industries, domestic companies get subsidies, etc. So we don't classify it as a war as such. We classify it as a limited denial regime because beyond the most cutting edge nodes, the trade between US, China, and others is going on semiconductors as it was in the past. Also, the war metaphor makes It is very difficult here because of this interdependence. Victors and vanquished can't be easily identified. In fact, all of them lose out if there is a sort of a decoupling. And finally, it's this usage of a war might preclude solution that will eventually help innovation, research, and supply chain resilience. And that's why this needs to be understood as a limited denial regime. Oftentimes, the communication of this as a war leads to foreclosing some options which are actually needed for building supply chain resilience. Now, the three reasons why we think semiconductors have become important once again from a geopolitical perspective are as follows. So one is the geopolitical significance. Of course, technology, as you all very well know, is now being seen by a large number of governments as a big source of power in this information age. Given that large-scale conventional conflicts are unlikely, large-scale economic decoupling is also unlikely because of globalization, even though we are seeing some reverses, the technology becomes an important domain where contestation can happen. So that's why this is one realization that a lot of governments are having. Second, the peculiarities of the supply chain, as I mentioned, where there are one or two companies in each part of the segment who are really at the cutting edge, also means that if those companies can be restricted, then their products can be denied to an adversary, right? So that peculiarity makes it useful as a tool to restrict some other country's industry. Third, Taiwan's centrality and vulnerability itself is an important driving force, and China-Taiwan relations worsening is driving a lot of things here. And there have been some concerns raised about hardware espionage, which is again leading governments to do industrial policy and try to build some of their capabilities back home. The second one is geoeconomic significance. Even if you forget the geopolitics, during COVID-19, semiconductor shortage became household knowledge for many people. The ripple effects were felt across a lot of industries, including automotives in Europe, for example, right? So that concentration risks are being realized by a lot of nation states. And forget about that, it's just also about geographic risk, right? So Taiwan has water shortage. What if there were a drought there? What if there are earthquakes in Japan, which often happen? All these things which have nothing to do with geopolitics can also lead to ripple effects across the industry. So that is also leading a lot of nation states to take some more active interest in this domain. And finally, the technological imperative as well. So whether we are talking about new AI chip architectures like TPU or successors to NVIDIA GPUs, a lot of new technologies also are built on top of advancements in chip architectures, right? So there is a technological imperative to having a good semiconductor industry as well. So in fact, in AI chips, you're already seeing calls for export controls embedded on as security modules on a chip. So these kinds of developments are driving a lot of nation states to take active interest. Similarly, when we are talking about EVs, there are compound semiconductors and new architectures being thought of which serve that segment well. So a lot of these things have combined together to make semiconductors an important domain for geopolitics to happen. Now, future and what happens next. So we tried to develop a framework to think of how this might map into the future. So if the strategic objective of a nation state is denial, these are the kinds of instruments that can be used, which are listed in the second column. And then we tried to look at some of the underrated repercussions of each of those instruments. Each of those instruments has a cost involved. None of this, I mean, the industry worked because comparative advantage based specialization did serve the world really well, right? So now if we are trying to reverse that for one or the other reasons, there will be costs, and that's what we try to list in the underrated repercussion section. denial. In denial, you're already seeing sanctions and controls and end-use restrictions, but we are also seeing a move towards outgoing investment screening and restricting movements of semiconductor talent. And that also will be an important hit if that happens. The second, if the goal of a nation state is not denial, but thinking in terms of outpacing your adversary, then the instruments that can be used are these as listed here. So for example, some nation states might try to do industrial espionage or targeted poaching of talent, but some other nation states might also think of building partnerships such that within a trusted ecosystem, you still have the chips that you need, but you're still able to outpace your adversary without having to do an autarkic localization in your own country. Indigenization and industrial policies already being tried. Some nation states might also encourage the movement of labor if the goal is outpacing the adversary. Within a trusted ecosystem, they might try this. But if the third goal is actually increasing supply chain resilience and not outpacing your adversary, just so that the concentration and business risks go away, then the instruments that can be used are even more interesting, like open source hardware. And there's a lot of work being going on here to develop open source EDA tools like Open Road, Open Lane, or even open source instruction set architectures, which can be alternatives to ARM. So this is something which EU and India, for example, are also quite interested in. Then to increase supply chains, you might actually do mapping supply chains, or again build partnerships such that you have resilience built in without necessarily having to do autarkic localization. These are some of the objectives which we try to map out. And finally, we sort of see this going as dependence on East Asia is unlikely to go away because of the really advantages that they have built over time. And similarly, the East Asian countries will find it difficult to build their own ASML or LAM research or other companies in quick time. So this interdependence is likely to continue. We do see that in the next 4-5 years, domestic production requirements will become inevitable if nation states are chasing localization. And in fact, we are seeing that happen in China. Just today, there was an announcement that the governments are trying to procure locally. So these are some things which might happen in the short term, but in the long term, it is unlikely. Consumers will have to pick the tab of this effort towards localization, and governments might have to keep funding and subsidizing in companies, manufacturing facilities, because obviously manufacturing facilities which are coming up in other nation states are costlier than what was happening naturally according to the market. So this is what we sort of end with, that a complete decoupling of the supply chain is unlikely. And we predict that this round of semiconductor geopolitics will perhaps end with some form of diversification, but also more importantly, a realization that semiconductor interdependence is a boon and not a bane. And that's why we end by saying that the chips won't be down for too long. With that, I end. Thank you.